Good morning, everyone, and welcome to the IBM Qiskit Live Quantum Seminar Series. I am thrilled to roll out this week's episode with Sona Najafi from IBM Quantum, who will join us here in just a minute. This is episode 116, and I'm very glad you've all joined us on time. So feel free to reply in the comment chat box, which is where you can ask questions of Sona live, where you guys are tuning in from. It's my favorite question to get us going and have a lively discussion. This seminar takes place every Friday at noon Eastern Time and will stay recorded, so you can always go back and watch Sona's talk, but we can only discuss and interact live in real time here. So with that, folks, I think we might as well get to it. I'm thrilled to roll out the latest episode of this seminar series dedicated to you, the research and academic quantum communities. I'm your host, Zlatko Minev from IBM Quantum Research. And I see that today we already have people from New York, India, Boston, Ecuador, Florida, and many other places. Yokohama, Bogota, the chat is still streaming in. So great to have all of these time zones and having you tune in from all these time zones and from all over the world. Now I have the pleasure of introducing Sona Najafi from IBM Quantum, who will speak on quantum machine learning from algorithms to hardware. Hi, Sona. How are you today?
Yeah, hello. Hello, everyone.
Great. And just let us know where you're tuning in from.
Yeah, I'm tuning from Cambridge, IBM.
Okay, wonderful. Before I let you go on with your talk, allow me to introduce you to our audience here. Sona is a research scientist at IBM Quantum. Before that, Sona was a research fellow at Harvard and Caltech, and she did her PhD at Georgetown University. Sona's main research interests lie at the interface of quantum antibody physics, quantum computing, and quantum machine learning. And Sona is the recipient of a number of awards, including a Google Quantum Award. So with that, it's great to have you here, Sona. It's great to see many familiar faces in the chat as well. From the Netherlands, from Boston as well, from Yale and others. So with that, the stage is yours.
Yeah, thanks a lot. Thank you so much, Zlatko, for the introduction. Myself, I'm a great fan of the seminar series, and today it's my great pleasure to be actually joining as a speaker. So I decided to give a talk about quantum machine learning from algorithms to hardware. And since I wasn't sure how many of people actually are familiar with the topic of machine learning, and in particular quantum machine learning. So the first 10-15 minutes of the talk is going to be very introductory. So I would like to start the talk by going through the history of the computing. That is, we might think that this is a recent subject, but it actually goes to very ancient time, as human beings were started to counting since 50,000 years ago, and almost there is some evidence of arithmetic tables from 1800 BC. Starting from the abacus, which was the simple arithmetic machine in 2500 BC, maybe two of the pivotal points in the history of computing, if we want to mention, goes back to 1837 with the analytical engine, which was the first programmable mechanical computer, and then later on with the Turing machine, which was the general concept of the computing. But the main breakthrough in the computation happens in the mid of 20th centuries with the invention of the transistors and also the development in the semiconductor technology, or the CMOS, which was the basic foundation of our classical computer. By now, our own smartphones has about 13 billion transistors, which makes them very powerful and more powerful than the computer in 1980s. But if we actually looking into the computational machines, maybe we don't really need to go that much far, because our own brain is a powerful computational machines, which has about 10 to the 11 neurons, and many processes are done in parallel. And because of the high connectivity in the brain, it's known that makes it robust to noise. And even though the time scale of the computations are 1,000 times is slower than the CMOS space, but they are very powerful in performing tasks like vision or motor control, which our computer and our simple algorithms are not capable of doing it. And this was the motivation, again, interestingly, in the mid-20th centuries for scientists inspired by the computation in brain to come up with the idea of the perceptron, and later on with the follow-up of the work by Rosenblatt in 1957, which actually formalized the simple perceptron. And early on in 1958, IBM made also a machine which was known as the first machine which was capable of having an original idea. However, also the breakthrough in the machine learning almost happened 70 years later as bigger number of data become available and we had access to more powerful computational resources, when in 2012, the breakthrough happened in the deep neural network, which capable them to have a image recognition and voice recognition surpassing human level. This actually brought us with the two elements of the computation being bits and the neurons. But then soon in 1960s was this question that as we actually make these transistors smaller and smaller, we're going to actually reach the atom size, and we might be actually looking for some other resources for the computation. And luckily, the nature is very kind to us, and that was the postulation of the quantum computing in 1982 by Feynman, that we can actually harness quantum mechanics, such as the laws of quantum mechanics, such as superposition, entanglement, and interference, to build a more powerful and a different paradigm of computers. So I think a lot of people who are actually joining us today are quite familiar with this subject. And for those who are not, we have tremendous amount of resources in Qiskit that they can actually look at. And since 1982 up to now, we have now different machines that are already developing to actually achieve both digital and analog computers. And for now, at IBM, we have like the biggest built-in chip, about like 433 qubits. And as a researcher, one of the questions that we ask ourselves, as this bigger number of qubits becoming available, what kind of task and what kind of problem we can target? And over the past few decades, there are different branches of research have been developed to actually trying to solve important problems in quantum simulation, quantum chemistry, or portfolio optimization, and quantum machine learning. And the focus of today's talk is going to be quantum machine learning. So at the interface of these three elements of the computation, the motivation is started by the question, what if actually this machine learning task can be actually run on the quantum hardware? And can we actually take any advantage of these noisy small qubits for performing some machine learning task? And that was actually the birth of the quantum machine learning. And before actually going to the different domain of the quantum machine learning, maybe let me explain in a nutshell what is a classical machine learning. A classical machine learning is a computational paradigm for discovering features in data and making some prediction. And as you can see, there are different elements in the classical machine learning models, one being data, and then we have to actually come up with the model that we actually like to train. And then we have a appropriate loss function depending to the task that we're looking at. And then we do some optimization and we update the parameters until we reach the target value or the task that we want to learn. So inspired by the elements of the data and the model, maybe many of you already see these quadrants. Maybe we can actually branch out all the different domains of the quantum machine learning. The first one having a classical algorithm on the classical data. So by now, many of you also are hearing a lot of news for the ChatGPT or DALL-E2, and also has a lot of also great success in the scientific domain, for example, for the data in LHC. The second domain that started early on was to actually applying classical algorithm for quantum tasks. There are different tasks, maybe using actually a restricted Boltzmann machine to learn the different phases or reconstruct the quantum states. And these are all can be considered as an accelerating quantum with AI, that you can actually find many of these different reviews in the following paper that I actually mentioned. But in my opinion, the most interesting part would be the part that we can actually apply and run the algorithms on the quantum hardware. And there are a few different motivations for that. And being that both the machine learning and quantum computing share some similarities, being high dimensional data, and also having some sense of inference and probabilistic. And that was the idea for the first domain of quantum machine learning, which was that we can actually speed up hopefully this quantum linear algebra that actually lies at the heart of many classical machine learning tasks, for example, for PCA or support vector machine. And the seminal work started with the HHL algorithm, which was a procedure to solve a linear equation in the quantum hardware. But soon there was like few caveats with this algorithm, one having like the quantum memory, and whether it's also not yet completely clear whether one could actually get this exponentially split up if we don't have the quantum memory. But also some other problems that we're facing is that currently we only have like like a small hardwares which are also noisy. Until we reach the fault tolerant and the big number of qubits, the question was that can we actually come up with algorithms that we can run on this hardware? And that was the motivation for the second domain of the variational quantum algorithms, which was closely inspired by the idea of deep neural network, which are the basic for many machine learning, classical machine learning algorithms, which are built by simple perceptrons that take some inputs and multiply by some weight, and there is some nonlinear function that has been carried out through the different layers, and depending to the task, one might actually optimize over some cost function. So inspired by the deep neural network, the idea of the variational quantum algorithms have similar elements, but with the different information flow, because now we want to do some hard part of the computation on the quantum computer, but we want to follow up the classical, the optimization on the classical computer. So it's starting with the input data that we have over here, then we have actually a parameterized quantum ansatz that now we're trying to train the value and the parameters of our gates such that in the end, after doing a measurement over the cost function, over a classical optimizer, we can actually do this iteratively and do different tasks. Some of the advantage of the variational quantum algorithm was that it was a very nice building block to actually perform multiple and different tasks. For example, if one writes down the cost function to being the Hamiltonian of some quantum many-body system or quantum chemistry, one can try to find the ground state energy, which can be used for the quantum simulation or quantum chemistry. But also one can encode optimization problem into some Hamiltonian, and this was the idea for the quantum approximation optimization algorithm. Or one can directly look at the distribution of the measurement and try to train the parameterized quantum circuit to learn some images or some pattern. But even though in the first glance, it sounds that, oh, this is like, sounds a very perfect match for the small and noisy quantum hardware, but soon there was some caveats and the challenges comes up. Maybe I can, there are many great works have been done here, so I apologize, I don't have the space or time to actually mention all of them, but I would refer you to following two reviews over here that list all of them. So the first being that like now we might have a problem with the data embedding, in particular for the classical data set. It seems that maybe achieving quantum advantage might not be that much straightforward. And also currently we lack of some standard quantum machine learning data set. But the second most important caveat and the challenges we face, it was this trainability and the issue of the barren plateau, because one starts with the most expressive ansatz being this random circuit and the random initialization, but this actually creates this problem of the training, because now one has to actually access to exponential amount of precision to navigate through the optimization landscape that becomes flat. So it's kind of, we're trying to find a needle in the haystack. And there was some follow-up work that are, connecting this barren plateau problem with the excessive amount of entanglement or global observable, which again, I will refer you to look at in the following papers. Maybe quickly on mention the choice of the ansatz and a lot of the different work that have been done on getting to, for example, considering some informal ansatz for quantum chemistry, but we might not have always information about our system. And generally, we might start with some heuristic or hardware efficient ansatz. And more recently, there are some work that actually try to build ansatz which are motivated by the symmetry in the dataset. And finally, of course, we have the noisy quantum hardware, and the noise can directly affect different elements of the training, and actually can destroy the inductive biases that are useful for helpful for the training. Motivated with all these challenges that we faced with the variational quantum algorithm, then physicists started thinking about, because in the classical machine learning, we have some paradigm of deep neural networks that are built and inspired by brain, and they are very successful in training, and also they are noise resilient. So the idea is that, can we actually come up with new method or new algorithm for quantum machine learning that overpass different problems that we have, very similar to the classical neural network. And this was, sometimes people call it brain-inspired quantum machine learning or quantum neuromorphic computing. And there are some works that have been done on the quantum memory cell or quantum reservoir computer, which in the last part of talk, I will go over it. So this brings me to the review of all the different domains of the quantum machine learning. And then in the next part of the talk, I'm actually going to start talking about quantum generative models, and in general, quantum neuromorphic computing and universal quantum perceptrons. So
maybe one quick question. Sure. Just can you tell us a little bit about the relationship between VQE and backpropagation, or how maybe that can help? As a question from Ron.
Yeah, so for the VQE, so that's a very good question. So generally speaking, over there, as I mentioned, the flow that we have over here can be actually different. So there are different ways that you can actually do the gradient descent. And in the case of deep neural network, we know that you can actually do the backpropagation. In the case for the variational quantum algorithms, there are different methods. For example, one is the shift rule. So you can actually look up on the shift rule, which would allow you to actually do exactly this differentiation for your variational algorithm, but it can become also costly because you have to actually perform many, many calculations. So is there any other questions?
Thank you. Yeah, this is great, folks. Feel free to post the questions in the chat. I think we have a very nice and active discussion here.
Great, yeah. So then let me start with the quantum generative model. So maybe many of you are already familiar with the discriminative model, which the goal is to actually maybe to try to learn some binary data, maybe a face of a cat or dog. But in reality, many of the real world problem that we are currently facing are not really discriminative, or in some sense, the data that we get doesn't have labels. Also, we are living in a very spectacular time, because now with all the invention in the development in the classical AI, for example, with the ChatGPT and DALL-E2, these are all models that are built on the generative AI, which enable to create some new content, including some new code or essays or text, images, poems, and all that. But also in the realm of science, for example, in physics, chemistry, and biology, and medicine, a lot of the data that scientists get do not have any label, and we usually have some, access to the probability distribution over some, given data. And the goal of a generative model is to learn the joint probability distribution over this data, and now create new samples from it. And the idea of a quantum generative model is very simple, inspired by the fact that the quantum mechanics itself is probabilistic. So if you actually write down the quantum state in some particular basis, we know that the coefficients of these different bases are attributed with the Born probabilities. And the idea is that if someone hands us some data from some experiment or real world problem, the goal of a quantum generative model is to find this quantum state in the Hilbert space that when we sample from it after the training, at best would be close to the target data that we have. But of course, if we actually write down the quantum state in any particular basis, generally speaking, the amplitude can be like a high-rank tensors. And the very first idea of actually the quantum generative model were based on tensor network, the ansatz that we built for our quantum state that encodes the probability distribution of a data. It was based on the matrix product state, because we already known in quantum many-body systems that the matrix product states are efficient representation of many systems. And also there were many different works have been already developed based on matrix product state or tree-tensor network or even parameterized quantum circuit. In a recent work, we actually showed that we can use this quantum generative model to reconstruct and do efficient quantum state tomography over a class of quantum many-body systems with system size surpassing 37 with the fidelity of 99%. But the more interesting question for us was that what other ansatz can be actually used for this quantum generative model? And this was kind of inspired by the fact that as I talk in like neuroscience, if we look at in our own brain, we can have different neurons that are acting or interacting locally or non-locally. But if we actually look in the quantum many-body system, we can have different phases of quantum many-body systems. Because of the interaction between the different degrees of freedom, we can have many exotic phases. For example, we can have disordered phases such as MBL or topological phases or some superconducting phases. And the questions and the motivation for us was that can we actually utilize these quantum phases of matter as a resource for learning? And as someone coming from the physics background entering into the field of machine learning and quantum machine learning, one of the interesting question that I face is that can we actually use different properties and different toolbox that we have in physics to better understand what is going on in underlying this learning mechanism? So for example, we can quantify memory, we can quantify energy, we can actually quantify different properties and aspects of the system, and maybe that way we can better understand what is going on with the learning. So this was the motivation for us to actually look at the MBL phase and why the many-body localized phase. This was actually a simple enough system that we can actually do the simulation, in particular for 1D, but also because of the disorder that we have in the system, this breaks down the thermalization, and people already over the past decades or so were interested to actually utilizing this phase for the memory. And the question that we were interested whether the existence of this like emergent memory in this MBL phase can be used for the learning. So the Hamiltonian is described by this ZZ and YY interaction, and on top each qubit that we have, we can actually couple it to some random disorder that is going to be the parameters that we're going to train. So let me explain. And it is known, for example, if the order of the disorder in the system, if we increase it to be bigger than 3.5, the system transits from the thermal phase into the many-body localized phase. So let me explain how now this quantum many-body inspired generative model works. Say someone hands you a data, and since we are very restricted with the small size, we take the downscales of the images, and we look at the pixel value, and we convert it to the probability amplitudes. And that is our data. But on the other hand, as an ansatz, as I mentioned, we have a chain of qubits, which is governed by the dynamic of the MBL. And at each spin or qubit, we have some strengths of a disorder. And the idea is that if someone hands a data that is attributed to this final quantum state in the Hilbert space, and we're trying to find, the goal is that we start with some random size 0 over here and evolving according to the dynamic of the MBL, and updating it, hopefully we can actually target that state. And how that it can be done? So we prepare 500 different realization of the disorder, which we can sample it either to be in the thermal phase or increase the disorder to transit into the MBL phase. And after one time evolution, according to our Hamiltonian, we sample from it. And we get the distribution over the model. So for example, something like this. And now we have some loss function that are just some measure of the initial probability distribution and the target distribution and the model distribution, and we minimize over it. So now we have 500 different realization, and we do a minimization over them, and we choose the one that give us the minimum value for the loss function. And we fix our psi1 at that point. And again, we do another time step and over 500 different realization and do the minimization and so on and so forth. And hopefully we can actually find our target state in the quantum space that is the generative model for the target task that we want. So let me, before showing you results, we also take into account, because in the classical machine learning, known that including the hidden units can also enhance the training. So we now, in our chain, we consider some of the qubits are actually hidden. And what we showed that if we actually can write the unitary evolution of our quantum system, and if we look at the boundary, the effect of this interaction of the hidden unit with the visible unit, we can actually ignore it. And what we can actually show that the probability distribution that we get from the visible, or in general simple Born machine, it's actually encoded in the hidden Born machine, or the hidden Born machine is superior in general in training and having the probability distribution over the vanilla Born machine. But someone could ask and tell me, oh, wait a minute, but now your model is disordered and it is localized, and how you can actually guarantee the expressibility of your model. And the way that we actually do it in our quench model that we actually training over the different disorder parameters, what we actually do, we now break down the disorder or our training values or the quench values with the time dependent and also time independent part. And we show that if we actually impose a pulse, that in the middle of the pulse we can actually have a pi pulse, we can show that this unitary evolution according to this particular pulse over here, what happens is that the this ZZ and XX, the XX and the YY interaction in the first half of the pulse and the second half of the pulse, they can actually cancel each other, and we reach to some effective Hamiltonian, which has been shown by my colleague Shungao that has a expressive power over the classical algorithm. So for a bipartite lattice in 2D, our MBA Born machine also would be expressible enough. So now
maybe a quick question there from the audience. So this is not adiabatic evolution.
That's a very good question. So in some sense, it might have relation to the adiabatic computing, but at each time evolution, we don't really follow any grounded state or anything. We only are evolving according to some target state that we have. Mm-hmm. So it's a kind of an evolution, but it's not exactly, I wouldn't call it adiabatic computing.
Okay, and maybe a quick comment around downsampling and using generative models in logic for downsampling.
You mean here in the sampling process? Okay, yeah, that's also a good question. So in some sense, I would call this quantum generative model as the implicit generative model. So what is implicit generative model is that it allows you to actually efficiently sample. The sampling in quantum mechanics is just for us a projective measurement that we do, and we get the values. But in some sense, because it's implicit, we don't really have an access to the original probability distribution, because we don't really know the quantum. If you want to know it, you have to do a quantum state tomography. Is that answer your question? Or maybe it's more on the data encoding, how the images is encoded into the algorithm?
Yeah, and Rajiv, feel free to clarify in the chat. But I think maybe that answers it for now. We'll let you proceed.
Okay. So now the interesting part is that, so we take the stiffened images of the MNIST data set. Now it's downscaled, and for each images, we do the amplitude encoding over the pixel value, which is converted to the probability distribution. And on the left, I'm actually showing a plot of the loss function, which is here is the MMD loss, which is just a simple loss over a probability distribution of a data and also your target model. And what we're actually doing on the x-axis, we're varying the value of the disorder. So interestingly, what we observe, if you're in the ATH phase, which is associated with the weak disorder, and the system is thermalizing, we were not able to train. And the moment as actually we increase the disorder in the system and we transit into the many-body localized phase, now the training is happening. For example, you can actually see how this images can be actually converged after many iterations that we had. And what other interesting is I give motivation is that hopefully by using different quantities that we know in quantum many-body physics, we were hoping that can we actually understand what is going on in the learning. So for example, the quantity here I'm showing in the middle plot is the Hamming distance, which is given by this equation, and it is known if your system is thermalizes because there is no correlation in this second term, it is going to be 0, and the value should be in the time evolution should stay around the half, and that is shown in the blue. But as what we can see in the MBL phase, because of the emergence of the memory and there is some existence of the correlation between different time steps that we do in our algorithm, there are actually now some value of the Hamming distance, hinting into that there is some sense of memory that is enhancing the learning in this algorithm. But of course, we were interested in to know, because the many-body localized state also is an interacting system. And here I'm showing the learning or the fidelity over learning the parity data set, which is known to be a very difficult data set to train. And I'm comparing 3 different phases. One is the MBL phase, another is the thermal phase or the ETH phase, and another one is the Anderson phase, where you actually, if you put JZZ to be 0, the system becomes 100% localized and non-interacting, even though it has a more powerful memory, but it seems that it not performs as well as the MBL, and that kind of give us an idea that the existence of interaction would be also important to allow the information to actually flow in the system and enhancing the training. So with that, I think that like this was part of a generative model that, we not only using the quantum properties for the training, but we're taking one step further. And we're looking in general into the quantum many-body phases and asking the question whether different phases can enhance the training and can we better understand that. With that, actually, this brings me to the last part of my talk, which is about this quantum neuromorphic computing and universal quantum perceptron.
And can you maybe just, before we move on, quick question, tell us a little bit more about the data set for the experiment and more about the quantum the hidden advantage?
Oh, here. So the data set, that's a good question. So here I'm only showing, so there were different tasks that we actually showed in the paper. So you can actually find it in this archive paper. Here, the very simple task that we actually look at, it was just the MNIST pattern. So we only take one pattern and we train over one pattern. So maybe I have to clarify that. And the way that we did it, as I mentioned, you take one pattern. For example, if you have an 8 by 8 pixel, now you can actually use 6 qubit to do the 6 different qubit to actually encode the amplitude. And for the hidden units, so depending on the number of qubits we actually see, we can actually encode maybe 2 hidden units. You can actually increase it. And maybe the question is that why there is an advantage in the hidden. So this is, you can think about as encoding, as including the hidden units into the Born machine. This has been also similar to what has been shown in the Boltzmann machine. When you actually hidden units and you actually trace out those, that can be actually enhance the learning. And this is a similar idea that we are following here. Or you can think about it that now actually this hidden units after the tracing out can be actually considered as a thermal bath for the learning or some sort of, I would say, random drive that could enhance the training. But I don't really have more than full understanding of why in general including the hidden units would enhance the learning.
Okay, thank you.
Mm-hmm. So that brings me to the last part of my talk, and then this goes in general, maybe a little bit motivated in the introduction, why in general we physicists and in the more recent years we're interested in this quantum brain-inspired or quantum neuromorphic computing. As I mentioned, we're currently at the stage that we have maybe a small number of processors, about hundreds of qubits, but they are very limited with the decoherence. And our goal is that we aim to actually perform some scalable computation with this, like, noisy processors. But on the other hand, we know from the success of deep learning that these are like at the heart, they are like some sort of an analog computation happening at the level of each neurons, which are also shown to be resilient to noise and disorder. And the dynamic of the interaction of this like neurons, it's such that at the end of the dynamics, some learning task is happening. So the motivation is that can we actually come up with quantum algorithms which are inspired by this paradigm that is happening in the classical machine learning, or in sense with the was motivated by the brain, and leverage the inherent dynamics of the quantum systems, but in the presence of the noise for the small quantum devices, and perform and do some machine learning task. So the very first simple idea is like the quantum reservoir computers, which was shown by the bunch of quantum dots, and they actually also shown that they can actually learn a entanglement of some quantum state. But let me explain you what is in general a classical reservoir computers is. A reservoir computers, it's a bunch of neurons, classical neurons that are interacting with each other, and there is some input, so you can actually stimulate some of the neurons and let the system evolve according to its dynamic and interaction. And after some time, you read some of the neurons, and you actually pass the data into some one layer of like simple neural network, and you train the neural network after measuring your reservoir computers. Because of this existence of this loop in the reservoir computers, they believe to have some sense of allowing some memory in the systems, and they have been shown to be really successful in predicting a lot of cognitive tasks. So naively, very similar way with the classical neural networks, we actually come up with the idea of the quantum reservoir computers or quantum recurrent neural network. But the idea is simple, that now instead of actually having a classical neurons, we can actually have a quantum neurons, and now we have qubits, and they're also interacting according to some dynamic. But also we now allow the system to actually have some Rabi, we add some Rabi oscillation or some actually interaction or coupling in the direction of the X to make the dynamic non-trivial. And we show that we can actually, in some limits, and taking into account this update rule that now is just like related with how much time we actually pulse each qubits, we can actually recover the classical neural network. So you can actually look into the details in the following paper. I won't really have time, but also we show that even with the simple combinations of 8 to 10 qubits, we were able to mimic many cognitive tasks. For example, decision-making tasks that is done, for example, for monkeys, deciding if the dots are moving left and right. And then we show the performance for the long-term memory and the short-term memory task and their association with the associative memory, and also some other interesting things related with the inhibitory and excitatory neuron and the fraction of having positive and negative weights in the reservoir computer. But I think what is more actually interesting, and the question was that if we can actually now allow this J-I-J interaction, which in the reservoir computer is kind of fixed, to allow them to be also trainable. So other people also look up this kind of paradigm in the framework of the quantum memristus, which was implemented with the superconducting qubits. But we also had the idea of the quantum universal quantum perceptron by quantizing this classical perceptron and allowing that the interaction can be actually changed and be trained. So in the rest of the talk, I'm gonna focus on the quantum on the quantum perceptron. And as I mentioned, the question we were motivated is that what is the most basic quantum unit that one could use for quantum machine learning? So we don't want to invent a wheel, so this is also motivated for the classical neural network, which is the building blocks of the classical perceptron And as I already mentioned, each neurons or the classical perceptrons, it's like get some input from the connecting neurons and does some weight and like some weights over it, and then does some nonlinear function, and it gives you an output. It's known that the power of the classical neural networks comes from stacking of many perceptrons on top of each other. So, of course, many other people were interested in the similar proposal. So there has been work that they tried to actually come up with the idea of the quantum perceptron based on some digital quantum circuits, or even utilize measurement as a way of to actually induce the nonlinearity in the perceptron. But one interesting angle that I actually also recently came across, it was from this paper. We're trying to look at the quantum advantage from the idea that maybe also alongside what having a quantum advantage and looking for algorithms that have quantum advantage, but maybe we can actually take some step further and look for some advantage which can actually also be encoded with the algorithms that are implementable, and also they are maybe theoretically tractable, and maybe there is some sense of modularity, and maybe they have a better training. And there was already some work that they actually utilized the adiabatic passage to mimic the perceptron, and that was kind of the motivation and the starting point for us to actually pursue the idea of the universal quantum perceptron. So as I already explained, what is the classical perceptron? The counterpart quantum perceptron, now naively, we substitute each neuron with the qubit. And now what happens for the input neurons is in input quantum neurons, they create a field on the output. But on top of that, now the field is in the z-axis, for example. We can also pulse it with another pulse in the x direction. And this can actually lead to some precision of this like qubits in the output, and we can actually have some like nonlinear output over here. As I mentioned, maybe we can actually look at the paradigm in the language of the Bloch sphere that we have over here. So we already had some field from the input affecting the output qubits, but also we can also pulse in the x direction, and that allows to persist. But the very first question was that the kind of a nonlinear function we were getting here was different from the classical one, and we wanted to recover the classical sigmoid function as well. So if we write down the Fourier transform of the sigmoidal function, this is what we actually want. And it turns out that if we actually know how to pulse in a different sequence of pulsing in the direction of x and the z, for example, in the series of the pulsing in the x direction and letting evolve the system in the z direction, we would be actually able to recover the classical perceptron. But so far, also one other thing that we show is that, for example, in this plot, we show that with increasing the number of pulses, we can actually recover our sigmoidal function. But also we can include the noise in the amplitude of the AK and BK, which was the Fourier transform that I showed in the previous plot. This can be considered as a decoherence noise or the dephasing noise in the system. And we can see that to some extent, this kind of existence of the noise in the output function is kind of resilient, even though now we have some wiggling, but the form of the function is not changing that much. And this can be actually understood from the fact that if you actually look at the Hamiltonian evolving with the Z and this X pulsing, up to second order is kind of insensitive to the existence of the noise. Now, we come up with this idea, and then we're showing that now we have some quantum perceptron that are implementable, and to some extent we can actually track them, and also noise resilient in the sense of the classical perceptron. But so far, what we only show is as good as what the classical perceptrons are. But the next interesting questions that we ask is that, but are they also universal? And are they capable of actually performing some universal computation? Because we know that the classical perceptron alone is not a universal approximator. And to do that, we can actually look at the entangling gate, which can be mediated between these two inputs by actually introducing this middle output So, I mean, I won't have time to actually go to the details of how this can be done. You can find it in the following paper. But also the single qubit gates is kind of given because you can only pulse in the Z or X or any other direction. And also the identity gates can be applied by actually allowing both input and output gates to be pulsed. So in a nutshell, we're able to actually, with the quantum perceptron, to implement all the different universal computation that we want. But of course, this comes with a cost that now we actually need to perform a lot of pulsing, which might be actually resource intensive. So in the paper also, we show that this kind of quantum perceptrons can be actually useful. We show that how you can learn or detect the energy measurement and also entanglement detection. And also it's some way we use it for the quantum metrology and also quantum sensing. But these are kind of very technical, and probably I would need another 20 or half an hour to go through all of them. So I would again encourage everyone to look at the paper. But with that, maybe I reached almost the conclusion, and I want to leave some room for questions and a little bit of discussion in the direction of the quantum machine learning. So I think some of the result that I have shown you, hopefully I showed you that like maybe we are at this stage that we have like this 100 number of qubits and they are noisy, and we're trying to find some tasks that are like suitable for this. And of course, like having quantum, we're trying to take an advantage over the quantum properties, but maybe we can actually take one step further and look into different knowledge that we have from the quantum many-body physics and try to utilize as much as we can the different exotic properties of the quantum systems. But also, I believe the main advantage that we want to actually look in the real-world application can only be happen by coming up with the algorithms that are inherently also directly related with the design of the hardware, and maybe we can tweak or we can think about like implementing this hardware in a way that are more neuromorphic or brain inspired, which are already shown much of success for the classical machine learning. And that was the idea for the universal quantum perceptron, and we shall see if it can actually be used for training real world problems. But of course, maybe still we are in the very early stages and we are facing many, many different problems. As I mentioned, the data encoding, this is actually a very serious problem for any real world application for many different kinds of machine learnings. That can be supervised or generative model or for quantum perceptrons. Trainability in general, that can be issue in particular for the variational quantum algorithm. And then we still have the effect of the noise, even though it might not be affecting at the level of each qubit, but as we know, as we increase the depth of the system, the noise kind of accumulates, and that can actually destroy all the advantage that we want from the quantum hardware. And as I mentioned, so what about like the connectivity of the qubits? What kind of architect and design could be suitable and useful for kind of task? So with that, actually, to brings me that I feel that we're in the quantum machine learning, taking any advantage of the quantum computers for the quantum machine learning task itself, it seems like in navigating through a non-convex landscapes, of course, is not easy. But I feel as much as it's not easy, is actually promising that there are much more interesting things happening over there, and it requires hard work and dedication for us to actually continue working on the field. And I believe that we might be actually seeing just the tip of an iceberg. So with that, I'll probably stop over here and give some time for a question.
Excellent. Thank you, Sona, very much. We had a very lively discussion chat and lots of questions. So folks, This is a great time to repost your questions as we get here to the final 10 minutes of Sona's talk and discussion. I think I'll start with, well, there's all kinds of questions here. So maybe one to start with is it seems there's a lot of interest in the experiments and code. Can you clarify again which parts were simulator or real devices?
Oh, sure, sure. None of the result I've shown you today was done in any experiment. These are all simulation on the classical. On the simulator. Yeah.
Okay, great. And do you want to tell us what your expectations would be around doing these kinds of experiments on the near-term devices?
Yes, good question. I think there are already, maybe I already mentioned, for example, the quantum reservoir computer. I believe some of them is already done with the quantum computers, different ones, quantum dots, and then also superconducting qubits, like actually IBM devices. We are ourselves interested in, like, following up with the idea of the quantum perceptron with the um, with the IBM hardware. I didn't show you here, but there is actually a circuit description. We map our quantum perceptron into a circuit description, so you can actually look at it in the paper. But there is some subtlety over here because it actually have some difficult gate that one has to actually apply. So that's an ongoing research to see how we can efficiently implement the universal quantum perceptron. And other things, as I said, even on the simulation side, we wanted to see if we can actually train the universal quantum perceptron for the real world data, maybe over images or some other data set. And that's ongoing work from the Harvard group. Maybe at some point they will have the paper out. So I hope that kind of answered questions on the ambiguity of the simulation or the experiment.
Mm-hmm. Yeah. And maybe on this slide, let's see, what is the complexity of the quantum perceptron?
Oh, that's a good question. So yeah, that's a very generic question. So
Maybe a
one
little bit of answer, yeah.
Yeah, like I'm not sure what they mean complexity, how it scales with the depths, how it scales with with the number of qubits and all that.
Yeah, there was a question earlier about how do the results improve also with the number of qubits, and what's the minimum number needed for good accuracy, at least maybe on the problems you've shown.
Yeah, that's so as I mentioned, a lot of the things we did because it's kind of a simulation, we only were able to do it about 8 or 10 qubits.
Mhm.
So unfortunately, we don't really have access over like at least on the simulation side. Of course, in the experiment, hopefully you will have access to big number of qubits.
And how deep were those? Can you remind us roughly?
I'm sorry.
How deep were those circuits in terms of C naughts or 2-qubit gates, I should say?
I don't have it. I don't remember how deep they are actually.
Maybe order of magnitude. Is it 1, 10, 100, 100,000?
No. It's kind of linear. So in terms of the depths, is linear in the number of the qubits, but it includes some implementing multi-qubit gates that one has to now decompose to some other gates.
Okay, so you have
And that is,
yeah.
actually, that is a calculation that we haven't done yet. So because I don't explicitly know what would be the right decomposition in terms of entangling gates. So the right answer would be I don't exactly know because we haven't done that part. Like we don't explicitly know what is the right decomposition of the quantum perceptron in terms of like entangling gates, but it requires a lot of them. In particular, if you want to decompose the multi-qubit entangling gates.
Mm-hmm.
So that's exactly the part that might be a drawback. In particular, maybe there's a smart way of doing it, and then, or maybe like trade off somewhere, and still keep some of the properties of the quantum perceptron, but substitute some of the multi-qubit entangling gate with the CNOT. But that's actually the next project would be.
Yeah, got it. And this is maybe to the earlier part, but there was a question around how many circuits we have to call in each iteration.
Oh, for the MBL part?
I think that was for the MBO part, yes. In other words, sort of what's the computational cost, if you want, there?
Again, that part we haven't done on the quantum simulation. So we have done the exact diagonalization.
Mhm.
So it hasn't been implemented on the quantum simulator. In that questions, because now when you take your MBL Hamiltonian, now you have to also trotterize it. So maybe another question related to that is that once you trotterize your MBL Hamiltonian, with what is the depth that you require to implement it for the time that you could actually train it and still not run out of your time difference. So any result I have shown is just based on the exact diagonalization on that paper. So it's not the circuit calculation.
Excellent. And this is maybe a
Sure.
far-thinking question, but is it
Sure.
possible to create a quantum chat GPT based on the idea of transformers? Is there a quantum transformer model?
That's a good question. Probably I'm not the best person to answer it. We are already in the few qubits trying to actually just show a simple generative model working. So ChatGPT or any other like a big AI model, I think we are far from them to being able to create them in the quantum. We would require huge amount of like qubits and efficient way of like data encoding and all that.
Mm. Excellent. And maybe this is again a high-level question, but
Sure.
the relationship between quantum machine learning and maybe using it for things like quantum chemistry to discover new compounds. Maybe if you give us a bit of a perspective on that.
Oh, that's a good question. I know on the classical generate. Oh, actually, I forgot also the acknowledgement. It's good. I'll put my acknowledgement. I'll say. Let me answer that question first. I know on the classical side, there are graph neural networks, and maybe there are some other methods that people use for, learning and creating new compounds. I'm not aware of any quantum. Maybe for small molecules would be, because still I don't know how one could scale it up. But definitely, yeah, if you can do it with the classical generative model, and if we assume that we're going to overcome different problems that I talk in terms of trainability and all that, definitely I think would be possible to come up with a quantum generative model that could actually come up with new compounds.
Excellent. Well, Sona, with that, I think we're coming here to the end. We've had a lot of really good questions. I hope I got to most of them. There was
Yeah.
a lively discussion today, and a few people said, thank you, really nice slides. We can see the chat afterwards.
Sure, thank you.
With that, I'll leave you if you want to share any final messages with us here in the last minute.
Yes, I think I would like to thank all my wonderful and amazing collaborators who have actually had the honor to work over the past 2-3 years. And most of the results, and some of them I showed, some of them I didn't really have the chance to go over all the different works we have done. But yeah, I wanted to take the moment and actually acknowledge them. Thank you. And thank you everyone for joining us today.
Well, thank you, Sona. Thank you guys for tuning in. This talk will stay recorded, so you can subscribe to the YouTube channel to know when our next upcoming presentations are. We have one, of course, next Friday at noon Eastern time, as always. And with that, Sona, folks, it was a pleasure. We'll see you next Friday.
Yeah, thank you.